Okay, morning guys. I believe we can start right now. It's been a while since we took a break from our class, and it's good that we've resumed. And bit by bit, step by step actions will always take us there. I appreciate all of you guys to follow through. For in the field of data science and machine learning, you really cannot learn everything by yourself, and the more you meet up and face different challenges and problems, interact with people, and go attend other meetups and listen to the approaches being solved and problems being solved by other people, the more you learn. And if you haven't reached that level where you can actually participate or contribute, where you're just learning the very, very basic, sessions like this ones really help, where we are mainly focused on the very, very basics to give you at least to give you like a roadmap of the areas that you need to look out for, and give you some foundations from within which you can do your own research, as well as now actively participate in several meetups. Through meetups, you will learn quite a lot of stuff. So I'm glad you guys are here, and today we're going to be covering statistics. I'm not so sure if you guys can see the screen, the slide. Anyone who can confirm having seen the slide?
Yeah, I can see it.
Okay, perfect.
We can see it. Go ahead.
All right, perfect. So, like I said, we're going to cover statistics, and before we delve into statistics, I'll probably just give you guys like around 5 minutes between 9:35 and 10, and 9:35 and 9:40, for us guys just to review what you can remember of from our previous class. We covered the very basics of machine learning, and we covered the types of machine learning, anything you can remember. I know we've had this session before, but this is a specific now to your group. I encourage open discussions. So we want us to review what we learned in the previous class. Anyone who can go first? Anything you can remember? So no one remembers anything from our previous class. The reason why I ask is there are some concepts I would want us to take through statistics while mapping, bringing out a few things that we learned in our previous classes. So if anyone does not remember, then I think we leave statistics and then I pull the other slides. We start from scratch. Yes, Deno.
Nauliza hii class tumekuwa nayo online or the last class before we put it on hub?
Okay. Before Rona came visiting, the classes we used to have physical meetups. Because you guys just finished beginner and you're just starting intermediate, and then we took a break.
From the current showing slide, naweza kumbuka mambo ya box plot, the quartile range ilikuwa kitu kama hiyo, upper quartile, lower quartile, yeah, and also central limit theorem. I can't remember exactly the definition of it, but ilikuwa something to do with acha kwanza niachane na hiyo probability. It's the nini inaitwaje, the likelihood of an event to occur. The other nini is theta and homo yenye iko hapo juu ya probability. Those are limitations.
Okay, okay.
Those are the limitations for linear regression.
Yeah.
Alafu kuna hiyo measure of shapes, skewness and kurtosis. Skewness is you can have right skewed, left skewed, and normal distribution. Hiyo if plotted, it shows how your data is distributed, or is the distribution of data.
Yeah.
Density plots. We cover density plots quick. Okay, sikumbuki.
Okay.
Histograms is also another method of visualization of data, ya kuonyesha how variables relate to each other.
Okay.
Yes.
All right. All right. That was a review of what we covered in. I think we must have covered statistics. I've just pulled it back as a good reference starting point. So we are going to cover this for those people who can remember almost everything. The better. If you can't, don't worry. We'll just have a recap this class. After statistics, now we'll proceed to other as had been planned previously. How about what we covered in with regards to machine learning before we started statistics? Robin?
Okay, what I remember is basically machine learning is, can put it a subset of artificial intelligence.
Mm-hmm.
So it's a form of artificial intelligence. I think they also, NLP is also a form of artificial intelligence. Yeah, just another example of artificial intelligence. Then we'd also dwelt on things to do like supervised and unsupervised learning, whereby I think for supervised learning, you're provided both the input and the expected output. But unsupervised is whereby you have an input, but you're not so sure about the expected output. So you try and find out the output from the input you've been given.
Awesome.
Yes.
Awesome. Nice. Any other person who has anything they can remember? Davy, from the previous class on machine learning?
I remember there were, in supervised learning, there was classification and regression, whereby classification dealt with labels. You already knowing, no, classification was whereby you had continuous, non-continuous data, while regression is continuous quantities of data.
Okay.
Yeah.
Okay. Non-continuous is, I know the word you're looking for is categorical.
Yeah, exactly.
Output. Okay. Okay. All right. Any other person? Alvin Karibu Sana. I'm not so sure you're in the first class. Anything you have to say? I'm not so sure at what level you are in. We might be a step ahead. So if you're in the class and you feel you are a step ahead, please just mention that so that we can, I can see the concepts that we can just pull through in this session so that you get a gist of it. Alvin? Okay. Looks like we've lost Alvin. Edgar? Okay. I think now we are in a position to proceed with the slides. That was a good review. And one thing you need to know is some of these sessions, it's good for you to keep reminding yourselves, because they won't change. The concepts and the words will not change, but the how will keep changing. So if you if you don't remember the concepts and the what, it will be difficult for you to explain the how, which is very, very radical. It keeps changing with time. Technology changes. How things are being done, how things are being implemented, keeps changing. So it is good and crucial that through such sessions, you remind yourself the what's and the basic concepts. All right. So in today's session, we'll talk about some intro to statistics, central limit theorem, descriptive statistics. It's good that this session was covered just before we went for the break. And anyone who has any contribution, feel free. I'll be throwing 1 or 2 questions to you guys so that it's more of an engagement. Because the session has been covered. So we'll also cover descriptive statistics, measures of shape, heteroscedasticity and homoscedasticity, probability. And then if time allows, we'll have a look at hands-on Jupyter. If we run out of time, then the Jupyter notebook will be a take-home. For us guys, the Jupyter notebook that was shared previously, you'll need to like review and revisit, and probably what I would recommend is for you to open a completely new notebook and try and reconstruct it. That is going to help us a great deal. All right. So statistics is split into, okay, before even we get a definition of statistics, I would like to actually define what statistics is. Anyone who can give it a shot? Okay, so basically what statistics is whenever you collect data, someone wants to try? Okay.
Yeah, I can try.
Okay, Edgar?
I can remember, if I can remind myself, that's the process of collecting information or data and presenting it. Now, in presentation, now it depends on various things, various ways. Then you, out of presenting it, now you draw conclusion out of it.
Okay, pretty much.
Yeah, I'm just trying to get some words if I remember myself. Yeah.
Okay, perfect. I think you're absolutely right, Edgar. And whenever you collect data and about any topic of your interest, and then you do any organization and probably analyzing, and that with the intention of interpreting it and giving value to whatever it is that you're studying. Yeah. So that is that process is what is called statistics, and the definition and understanding of statistics may vary, but the fundamental of it is the same. Yeah. So Edgar, you're absolutely right, and we might want to ask ourselves why is it important to study statistics? One is because just like any other subject, we just want to be knowledgeable about statistics and probably be competent in statistics so that we could either offer advisory. And another reason could be we actually want to interpret and critically evaluate statistical information. So there is a lot of data outside there, and there might be need for such expertise to that level for interpreting and critically evaluating that information. Yeah. And then finally, if we want to make inferential conclusions from that study, yeah, by using what is called empirical evidence. Empirical evidence is basically from the observations that you make. That is what I mean by empirical evidence. You make certain observation and then you infer statistical conclusions from that empirical evidence. So it is conclusions based on some evidence. So those are some of the reasons why you might want to study statistics. And later on, as I give examples, for as I explain the statistics, then I'll actually also go through how statistics blends with machine learning. And that's why I brought up the previous session where I asked you guys to like try and remind yourselves certain concepts about machine learning, because in this one, I'm going to give examples. So we have descriptive statistics and inferential statistics. Yeah. So whenever you get certain information, I think I've alluded to inferential statistics, where based on the study you've done, you infer. We are headed to a period where we are going to see a lot of political activities, and there'll be both a lot of surveys being done and conclusions. And I think we can remind ourselves what normally happens, that 70% of Kenyans like what the government is doing, 40% of Kenyans did this and this and this. That is a conclusion based on a certain survey. Whether it is skewed or not, whether it is biased or not, we really can tell until we do another research by ourselves to counter what is being said. So that is the beauty of statistics. It is only true and conclusive based on the study. So if you want to dispute whatever results or whatever inferential conclusion someone else has come up, you have to do exactly the same thing and do a study, sample the data, and do the study of based on probably the survey you did, and come up with conclusions. If it differs, then you can conclusively make a counter statement. Yeah, and this is a process. So you might be wondering, how is it possible that one person or one study gives these results, and someone else comes up with a similar study and gives a different results? If you look at the start to the end of the process of statistical studies or empirical evidence studies, yeah, you will get to appreciate why there is room for those results. It depends on what you find from your sample. And speaking of samples, the first and genesis of, basically from what I've said, I think you guys now get the gist that the study is based on a sample data set. So this sample is extracted from a population. So for instance, let me put this into context. If the population of Kenya is 40-something million, I think we're headed to 50 as per the last results. Anyone who has the exact figure? I think the results were out. Anyone who has the exact figure?
I think we're about 47
47 million, yes.
Yeah,
so let's work with that for the sake of the class. So approximately 47 million Kenyans in how many counties? I think we are, how many counties are we? 41?
47.
We are also 47 counties. What a coincidence. So someone would just say it's 1 million people per county, which is not true. Yeah. So we are 47 counties, we are 47 million, and then each of these county has certain geographical space. So we have smaller counties, we have bigger counties, we have largely populated counties, we have sparsely populated counties, maybe in the arid areas like Wajir. So, and we have different geographical, clearly geographically in terms of climate and everything, it's different from one area to another. And the infrastructure is also very, very different, yeah? And Kenya is very, very big. So you can imagine if you were to talk to each and every person about whatever study we want to make. For instance, do you like the current government or not? Or do you like Ayub or not? Or do you like whoever, a celeb, whatever questions you want to come up with. Imagine walking through all these counties, speaking to 47 million. It is ridiculous. By the time you're getting to the 47th million person, at times will have changed, preferences will have changed. Probably the question you're asking will also have changed. As in, you ask me this question today, and then say after 6 months you're in Wajir asking the same question. On the 6th month, I changed my mind because the government has actually satisfied my need. So it is practically ridiculous to try and think of doing a survey to an entire population because of the explanations I've given, and it is also very, very expensive. Yeah. So having said that, statisticians, or the best way is normally to find a way of sampling the people you want to study. So the sample is an extraction from the population, and there are several sampling techniques. So whenever you sample this and you create a sample and you survey or ask whatever questions, you get certain answers, and then you decide to plot some visuals just to understand what most people are talking about. Now, those visuals like graphs, bar graphs, pie charts, like let me say what's the percentage of men that were responding to your questions as compared to the percentage of women. Now that you would probably display through a pie chart, which is best suited for visualizing proportion in any sample. So the moment you get that and you want to inform more and more about what you've collected, that is inferential statistics. That is descriptive statistics. So you're trying to get an understanding of whatever study you're doing, yeah, before you come up to a conclusion. Once you do that study, and then oops, all the sample you're studying, based on the techniques, you come up with a conclusion that, hey, all right, I spoke to 2,000 people cutting across the entire constituencies of all the constituencies of Nairobi. And according to these people, I think they are confident with what the government is doing about Corona. And that figure is, say, 68% of Nairobians feel they are confident with the efforts being done by the government with regards to Corona. So that conclusion is inferential, yeah? It's inferential. It's actually inferring to the information that you collected, and you're now concluding. Now, if someone else feels different, they need to go through the same process, create a sample, and the process that is well explained through statistical means, and come up with a conclusion. And statistics, the beauty of statistics is it allows for that difference, and you need to be able to explain it. And then later on, we'll be talking about confidence level or confidence thresholds, and with certain confidence, you need to be able to make those inferential. Now, another good thing about statistics is, or the anchor of the study of statistics is that it is believed that should you pick several different samples from a population, then the variance of the statistical measures remains the same. Yeah. So that is a study done by some genius somewhere, way so many years before most of us were born, and it has been believed to. No one has come out to dispute it. So it is actually a study. And as one of you guys had mentioned earlier, I think he only forgot that was Dennis, central limit theorem. So statistics is pegged and anchored on central limit theory. So the statistical measures do not differ sample by sample as you pull different samples from an existing population. So based on that, it is believed that should someone else do the same study, picking different samples, using different sampling techniques, the variance or the difference will not be significant enough to derive a different conclusion. But if the difference is significant, then they are able to derive their own conclusion and put their approach for debate and contestation, and the cycle continues. So there is another word that I've brought up, which is significant. We will also look at this when you're doing hypothesis testing, which is another study within statistics. So I've explained what descriptive statistics is and inferential statistics is. And I've also introduced central limit theorem. Yeah. So if you allow me just to read what was there, though I've already explained it, given an independent and random variable with a sufficiently large sample size, the mean of all samples from any given population will be equal to the mean of the population. So if you derived 4 samples from a population and calculate some measures, for instance, like the mean, or yeah, the difference should be insignificant. So that is the anchor of central limit theorem. Yeah. Okay. I've also mentioned descriptive statistics. The way I had mentioned about you guys getting the mean, doing plotting graphs, bar graphs, pie charts. Pie chart is ideal for proportionality. Like now you want to check proportions, and there are other ways of describing your statistics. Like now, looking at the distribution. Yeah. When you look at the distribution of your data, you're also looking at, it's actually descriptive statistics. That is what you're doing. We will cover distributions. When you understand how the distributions are skewed, is it left skewed, right skewed, is it normally distributed? Yeah, all these have significant interpretations, and they have impact on how you're going to conclude your model. So when you look at your data set with a certain skewness, what is the probable impact of that skewness to the interpretation of the results that you get? And that is why descriptive statistics is very, very important for machine learning engineers. So you need to be able to get some descriptive statistics out of your study just before you start modeling. And as I will show you later, and or probably you've written Jupyter notebooks. Modeling is not difficult because we have libraries and tools that enable us to do. If you guys remember .fit and then you .predict. So basically that's it. After you've gotten all the data that is now ready for doing predictions, all you need to do is to call a .fit and .predict, and you have your model there. Then you start doing predictions, and then you interpret the predictions using confusion matrix and classification report. So the biggest and the most toughest place is the statistical part, data preparation part, the inferential statistics, descriptive statistics. That is where a good machine learning engineer would probably take time with data. And then after taking time in that part, then you need to do modeling. And when you're doing modeling, you can iterate. Since you got the first part right. You do the first model, poor results, you iterate in doing your modeling. And the iteration is guided by either optimization techniques, depending on the algorithms that you're choosing. Each of the algorithms that you choose have different techniques of optimizing. So that is where statistics blend with modeling. And there's something I mentioned in the previous class where a model, this should actually be your 1 + 1 is equals to 2. Yeah. So if you cannot forget 1 + 1 is equals to 2, try and not to forget this. Algorithm plus data equals to model. Yeah. So if you want And algorithm is basically statistical and mathematical techniques that have been embedded or packaged together in a library. So we are studying statistics with the intention of understanding how these algorithms work. And later on, it's going to also help us in understanding how we optimize these algorithms for us guys to get better performing models. So we have statistical techniques embedded inside the algorithm, and then we have data somewhere. We combine the data and the statistical techniques. The statistical techniques will now study the data using mathematical techniques, formulas, Once the algorithm studies the data, it will derive a model which understands that data, and with that model, you can now do your predictions, because the algorithm understands the data that you've exposed to it. There is so much now from your model. You realize that there are some good performing models, there are some poorly performing models. It means that either the algorithm understood in large extent so much about the data that it was given, but when it is exposed outside, it performs poorly because the new data, it is new. That is another term where we are calling overfitting. We will come to that section, and we will actually cover the things that I'm talking. But the reason why I'm raising this right now is for us guys to understand where statistics play and why it is such an important field when it comes to machine learning. Okay, so other descriptive statistics that we have mean, median, mode, standard deviation, variance, skewness, kurtosis, interpercentile measures, and range, as you have seen on your slide. So this is where I want us now to try and remind ourselves, and it's an open book question. Who can just pick one of those descriptive statistics and explain to us how anything about them? I think the floor is open for anyone who wants to go first. Okay, I'm going to pick three people to randomly just pick 3 descriptive statistics, and then we move to the next slide. So Silas, pick any of the descriptive statistics and then tell us.
Hello?
Yes, Silas, go ahead, we can hear you.
Sorry, my network has been on and off, right? I didn't really understand the question, but what I can say is that based on the data that you have, you'd need to be able to look at what the mean and the standard deviations of the data formats that you have when you're investigating. I don't know whether that was what you're asking about.
Yes. I just wanted you to pick.
So you need to understand how far the variance is between the data and how your data looks. So when you're doing the investigations, you need to see the data composition and see how far the outliers are and the means are, right?
Okay, absolutely. So it's important to just get an average of the data you're looking at. The average is what is called the mean, and then you check the standard deviation, variance, statistical measures. Let me pick someone else. Alvin, are you back? I think you've been struggling on and off, in and out of the meeting. I don't know if we have you now. Alvin?
Yes, hello.
Hi, Alvin. Welcome back.
I'm fine. Thank you. I'm sorry, my network was a little bit bad. But this is my first class, so
okay.
I'm just following in the background.
All right.
So I've done a little bit of Python and data science, but I started using it's called WQ.
Sorry?
I'm saying.
Yes.
I've worked with Python a little bit.
Okay.
So the platform I was using was WQU. It's a online school.
Okay, okay.
So I'm glad to be here. Just want to capture what you're teaching.
All right. Karibu sana, Alvin. So in case it's a bit deep, feel free and ask for clarification. Because there was a previous session that we had covered, I think 4 Saturdays, where we covered machine learning types, quite a lot of stuff, intro to machine learning. So if you feel lost, feel free to ask, but you don't need to worry. As we move forward, I'll be bringing back those concepts, and we will actually revisit those concepts, but now at a higher level.
Okay, thank you.
All right. The last person I'm going to pick is Deno. Deno, just pick one of this and just tell us what you understand, one or two, what you understand, what it does, and yeah, we move to the next slide.
That is skewness.
Okay, skewness.
Actually, it's, for skewness is divided into 3. There is left skewed and right skewed and normal. Left or left skewed means that the data is more away from the mean, or is not centrally packed together. In the means of positive and negative positivity of the skewness. So if the data is left skewed, it means more of the data is huko mbali, away from the mean, or the mean is pulled by the much higher values. If huko is most concentrated to the values which are values of low, whatever. I don't know. That's how the words to
the exact sums. Okay.
Exactly.
But I get the concept. I don't know if there is anyone with a question. I think you're getting it right. We have positive skewness, negative skewness, and a normal distribution. When there is a positive skewed, the tail is longer towards the right, and when there's a negative skewed, the tail is longer towards the left. And what that means is the mode is greater than the mean for negative skewed, and positive skewed, the mean is greater than the mode. So there is a way you need to look at, you need to look and understand the skewness of a distribution, because you'll be building distribution plots for your sample data or for your descriptive statistics, and you need to be able to understand what is the possible impact of that skewness when it comes to your model. Okay. All right, let's move to the next slide. And there is one very key descriptive stats that I felt that needs to be spoken a bit as a topic. Interquartile range. So it is a way of measuring also visually, detecting actually outliers, but using an interquartile range, you can also tell how skewed is your data. Is it positive or negative? Though it will not visually represent that. The main understanding of an IQR is to be able to detect outliers through a box plot. So outliers, basically, outliers is the observations that more or less stand alone. So assuming you have a list of records in an Excel sheet, and then record number 9, and this is a list of, say for instance, everyone in this class. And record number 9, and assume, let's say, we assume it's, we picked 10, a sample of 10 from the class, and record number 9 has one feature that is way out. And for example, the features that are in this Excel sheet is the name of the student or the name of the participant in the class, the age, the birthday, and probably what they take for breakfast every morning. Yeah. So if the age of the participants, when you skim through all the 10 records, you skim through, you find someone is say 992 years. Yeah. If those were days of Abraham and Adam and Eve, then it would be possible. Yeah. So let's take two cases where, yes, we've gone back to the days of Adam and Eve, and it is actually possible to have an age of 992 years. Yeah, so let's work with that as a first scenario. In this case, and you see that all the rest, they are ranging between, say, 90 years, 80 years, 40, and then the maximum from the rest is 100. So this 992, while it is true, it is alone. It is alone, as in it's what we call an outlier. Yeah, that is the first scenario. But let's fast forward to 2020. We are no longer in the days of Adam and Eve. In 2020, is it practical to see even someone with 200 years? It's not possible. Tuko na ugonjwa, corona inapambana na wewe. Everyone wants to take you 6 feet under. Everything, including human beings. Everyone wants to pull you down, and including diseases, lifestyle, magari ile unaendesha, hiyo pia inakuambia na kupeleka huko kwa baba. As in, you're fighting with nature. So if you get to 200 years old, you're actually lucky. You can actually enter into this book they call the Guinness Book of World Records. We have a few people above 100 years. So if that is the case, then we can only explain it by assuming that this was a typo error. It is a typo error, and depending on the explanation you give your observation, it dictates the decisions that you take. So if it is a typo error, you could remove that observation from your data set. So you remain with data that makes sense. If you are in the days of Adam and Eve, then you will still have it there and make choose one of two things. Either just model and observe, build two models. You build the first model with that data, the second model without that data, and then observe the impact of that. Or you could, if it is a feature that you can actually scale, you can use techniques like standard scaler. So those techniques, we'll talk about them, where you create a new scale that neutralizes the impact of the dominant numbers. In this case, that 990 something is really, really dominant. So there are techniques of neutralizing the effect they have on whenever you're coming to modeling. So now, I was just talking about 10 records. What I mean is 10 observations. Observation is equivalent to the rows in an Excel sheet. So if, assuming you're working in a company that, or the study has a lot more data, because there is normally, in this field, we study a lot of data, say millions of observations, yeah? How would you easily pick these outliers? Yeah. So there is a technique called a box plot or interquartile range. Box plot is to visualize and see where these outliers are. And interquartile range is a technique within which you can actually identify these outliers and either implement or neutralize them or do whatever you want with them based on what I've explained. So this is a very, very important visual. You need to have it in your notebook. And most importantly, you need to know how to detect the outliers using interquartile range technique. Yeah. All right. So when you're calculating or detecting interquartile range, there are several steps, and they are projected right now. I want to pause here and give someone who can remember these steps in class to walk us through how we detect the outliers. Just feel free. If you get it wrong, then after this class, you'll never forget it. If you get it right, then we are all together in this. It will make you feel like you're learning. So when you get it wrong, you're still learning. When you get it right, you're actually learning. So I want to take someone. Anyone who can walk us through this?
Ayub.
Yes, yes.
Okay, let me just know if I can remember. You divide the data into two, or the data set into two after you have arranged it in ascending order or descending order. After that, you find the median. From the median, you have two sets. You have the any continuous median and any continuous median. From the two sets, you divide each of them katikati tena.
Yes.
So the lower side you have your Q1, which will be the value katikati.
Yes.
After division.
Yes.
The same applies to the above side, which will be your Q3. Then there was the formula of finding the upper fence or the boundary, which will be Q3 yenye tumepata from getting the median of the upper side, plus Q1 QR ilikuwa QR ama ilikuwa 1 QR something, ilikuwa kina kitu kama hiyo, and then you multiply by 1.5. The Bodmer's rule will apply there, and then it's the same for the upper fence, but now you will be adding Q1 instead of Q3.
Okay. Thanks, Deno. That is absolutely it. You've explained it. So what IQR is interquartile range is what you get the third quartile less the first quartile. That is interquartile range. And then the margin, to get the upper fence, you multiply the outer fence, you multiply them by either 1.5 or 3, depending on the option. So if you use 1.5 to do the calculation, then you will get your outliers. If you use 3, so it creates a band. It creates a band of all the mild outliers. Anything above the results you get from when you multiply by 3, these are extreme outliers. So you can decide to use both and consider the extreme outliers as the ones that are outliers, and you can choose either to drop them or not. Okay? So if it is not clear, that is a concept that you need to really practice, and you can reach out to any one member of the class or even to myself, and it will get clearer. You can we illustrated this in class on a whiteboard. I could probably repeat it the day, maybe in future classes I'll add whiteboards so to explain some of these concepts. And the next slide actually the steps that Dennis took us through. Yeah. From the data set, if before you could do calculations, there are people who would feel 17 is an outlier. There are people who would feel 17 is not an outlier. So the question is 17 an outlier from what you see? And you need to have a technique that actually convinces everyone that it is an outlier. So there was need to come up with that technique, and that technique that has been adopted is IQR. Yeah. So you first calculate the inner fence, you calculate the outer fence, and then you do your calculation. and the conclusion that you come up with, it is 17 is neither a suspect or a strong outlier. Okay. Any question? I've gone on and on and on. I want to invite guys with either a question or a comment or an additional or even a subtraction. If you feel I've said something that is confusing and you want to clarify, you can go ahead and clarify.
That last concept is a bit confusing to me. Or maybe when I look at the slides, a bit confusing to me. How do you create an inner fence value? What does -5 and 19 mean?
All right. So inner fence, let's walk through this example. What is the median of this 1, 3, 4, 6, 7, 7, 8, 8, 10, 12, 17? What is the median?
Okay, it's understood. It's 7.
No, I
right?
want us to walk through this so that we this is what I did in the previous class. So I want us to walk through this to the extent where we will derive -5 and 19. So anyone who wants to tell me what the median of these observations is? Anyone?
The median is 7.
Okay, perfect. I was almost getting scared because it's an open book. It's right in front of you guys. So I don't know. But the way, if you don't know how we derived, we came up with 7 as a median. You count, you need to split this list here into 2. And exactly 2 values on the right, 2 values on the left. So to our advantage, we have 11, which is an odd number. So we just need to make sure that we have 5 records on the right and 5 records on the left. So the median is 7. Now, Dennis had explained, you have to now get what is you split it into 2. Let's come to the first. There's a lot of noise coming from somewhere. Okay, that was Silas. All right. So let's split this into 2. We take the left side and split it into 2, and then we take the right side and split it into 2. So the left side, when you split it into 2, we look at what is the median here, which is equivalent to the quarter, the first quarter. The median is 4. And when you take the right side and split it into 2, the third quarter is 10. Yes? So what is the interquartile range? The interquartile range is Q3 minus Q1. Yeah? So Q3 minus Q1, 10 minus 4 is 6. So the lower bound, the outer fence, or rather the lower, let me say the inner fence is the value. You deduct 6 from 1. It will give you a negative number. 6 from 1 gives you a negative number, which is -5. So this one, all values, it's helping you to get the fence on this other side for the values that will not be considered as outliers. So 1 minus 6 is -5. You get -5 as the inner fence. And then on this other side, you need to, is it from Q3? It's actually from Q3, inner fence. Interquartile range is 6, inner fence, yes. And then from Q3 is 10. Values 10 minus 1. 1 minus 5. 3 plus 6. It's 2. So when you're looking at 19, you do the same. You did the same calculation using. You use the same calculation using 3. When you do the calculation using 3, let's work with the out of fence. 3, negative 14. Repeat. Negative 5, negative 14, 19, 28. Out of fence. 6 plus 23. I think this calculation has an error. Just give me a minute. Let me just review it again. No, I think it's correct. Let's just do it. We are supposed to be doing 1.5 times interquartile range and then getting the inner bound, inner fence, and outer fence. That is what was confusing. But now, let's just do the calculation. 1.5 times the IQR, basically 1.5 times 6.
That's 9.
Now, 1.5 times 6 is 9. And our lower boundary was 4. So when you do 4 minus 5, what do you get?
4 minus 5, 10.
See, 4 is this one. Remember the Q1. So we need to get the range. Which number on this side will create the lowest bound? So 4 minus 9. 4 minus 9 is negative 5. So we get our lower bound as negative 5. And on this side, the Q3 was 10. So 10 plus 9, it gives you the upper, yes, it gives you 19. So valid numbers, the valid numbers is from negative 5 to 19. If you had a number that is 20 or even a negative 6, those would have been outliers. Silas, does it now make sense where negative 5 and 19 is coming from?
That makes sense. I think the next case is about the outer fence.
All right. Now, for outer fence, we are looking at doing the same calculations using 3. Excuse me. Using 3.
Instead of 1.5, you use 3.
Absolutely.
No.
Yeah. Yes, Dennis?
I think you did not get his question.
Okay. Just rephrase it.
See, Ayub.
Yes.
On the actually nikaa mimi nimechanganyikiwa. I thought when you are looking for strong outliers is the nini unatumia 3.
Yes,
3.0.
exactly. Yes, that's correct.
So that happens on the upper side of the median after you split your data. Ama you use both sides 1.5.
I think what is confusing is these words here, inner fence and outer fence. This one, it should be mild outliers. This one is strong outliers. I think that is what is confusing.
Yeah.
Because you see, this one is,
I think so.
yeah, this is what is confusing. This should be mild outliers, and this one should be strong outliers, because this one is the inner fence, this one is the outer fence. So now 19 is the outer fence, the topmost value on this side, and the inner fence is the lowest value on this side. So that range is what we have valid numbers. Anything outside becomes an outlier. So I'll correct that.
Are you?
Yes, Robin.
Just kindly again, just repeat how you reached to negative 5 and 19, kindly.
All right, no problem. So if we start from getting the median, so let's say these were the ages of all the students in class, sorry, yeah? So you first sort them out from the youngest to the oldest, yeah? Assuming age number 1 is just a representation. We cannot have 1 year old in class of machine learning. So, so this, we pick the median, the number appearing right at the center, which is this, 7. And then after picking 7, we get, now we have 2 groups of data. The first group this side, and the second group at the top. So the numbers at the top, we need to get the middle of those numbers, yeah, which is 10. Which one appears right at the center? Because at the top we have 5, at the bottom we have 5, the bottom of 7. So these are 8, 8, 10, 12, 17. If we split these 5 into 2, we'll have 2 values on this side and 2 values on this side. 10 becomes the center. But if it's in reference to the entire list, this one becomes the upper quartile, yeah? And this number 4 becomes the lower quartile, yeah? Basically Q1 and Q3. So the objective is to get Q3 and Q1. Once you've determined what Q3 and Q1 is, we need to get the IQR, interquartile range. So interquartile range is normally, you get the Q3 minus Q1, which we've determined to be 6, yeah? Now, there is something called the mild and strong outliers. To get mild outliers, you use 1.5. It's a formula, it's a standard formula. You multiply the interquartile range you get by 1.5. So in this case, to derive the inner fence, okay, first we get the interquartile range times 1.5, you get it as 9, yes? So 1.5 times 6 is 9. You now come back to your list. The Q1 is 4. So you want to get, what are the valid 9 values from Q1? So you need to calculate this range. So the way to calculate that range, you want to get the valid values up to what value are the numbers valid, then they won't be considered as outliers. So that would be 4 minus 9, which you get -5. So your inner fence becomes -5. Your inner fence is this. And your outer fence then becomes, you get this, yeah? You add 9, the interquartile range that you calculated. 10 plus 9, you get 19, yeah? So any value outside 19 become your mild outlier. Anything suspect outlier, yeah? Anything above 19. So the question was, is 17 an outlier or not? So because it falls within the upper fence, then 17 is not considered as an outlier, but 20 would be considered as an outlier, considering this data set. Does it make sense?
Yes, it does.
All right. Okay, so outlier detections and handling in your data set is very, very fundamental. And the best way to visualize your outlier is looking at the box plot and using interquartile range to detect the exact values. And then once you've detected the exact values, you can actually either remove them or handle them in a different way. Yeah. We will cover those when we are looking at now. When you're looking at machine learning, we will definitely have notebooks subsequent to these classes. All right. Okay, we have a frequency of data and histogram. You need to like visualize the distribution of your data. So a histogram, basically it takes your data and splits them, puts your data into buckets. Yeah. So it tells you when you're building a histogram, ideally you just want to see in your class, for instance, how is the data distributed? Do we have most guys who are older, or do we have most guys who are younger, or is it like it's just normal? We don't have any of those. So for instance, if we split our class into 3 bins, so basically 3 buckets. So the first bucket would probably contain ages between 1 and say 6. The second one between 6 and say 12, and the third one will be between 12 and say 17. So of course we are understanding that there is no child age 1 in class, especially machine learning class. So these are just representation. You can decide to add say 8 years to each of those numbers. So let's go back. We can decide to add number eight to each of these. Okay, oops, we'll have people 178 years. Okay, let's add 18. Yes, let's add 18 to each of this number. So the first age would be 19. The second one would be 21.
21.
Yeah, the third one would be 18. 22. Yes, and then the oldest would be 30.
18 plus
35.
35.
Yeah, the oldest would be 35. So we can decide when we want to see if we split this data into buckets, will we have guys who are older, majority, or guys who are younger, majority, or it's just normal? So let's split it into 3 buckets. The first bucket is up to here. The second bucket is up to here, and until the last one. So you'll figure out that this one forms a normal distribution because you'll have 1, 2, 3, 4. 4 guys who are aged 18 plus 6 is 24.
24.
Yeah. So we have 4 guys who are aged between 19 and 24. And then we have 1, 2, 3, 4, 5. 5 guys who are aged between 25 and 28. 5 guys. And then we have 2 guys who are aged between
above 30.
30, above
and
30. Yeah.
Above 30.
So if we have 4 here and we have 5 here and we have 2, so it will go up 4, and then when it gets here, it is up because it's high, and then it comes down to 2. Yeah. So it is more when you're plotting, it goes like it is a normal distribution. But we will have instances where we have okay. Yeah. We'll have instances whenever you plot your histogram and it doesn't portray a normal distribution, you'll now start seeing things like skewness, what Dennis was saying. You might find that this class, we have 12 guys who are between age 19 and say 25, and only 2 are aged between 25 and excuse me, between 25 and say 30, and only 1 person above 30. So that is skewed. Majority of the guys are in the first bucket. So that is the pattern that will be articulated whenever you plot a histogram. It's a very, very important graph to have in your descriptive statistics section of your notebook. Excuse me. Hey, nani
Corona.
Aisha?
Corona.
Wacha hiyo, tema hiyo mate. I'm healthy and kicking. All right. I think my throat is just dry. I need to have a thermometer to take my temperature. Some of these thermometers in supermarkets, I highly doubt they're working. The other day I walked into, and if they're working, I have no idea. I don't think those guys know what they're doing, because I came from a house, I think 2 days back. I went to the supermarket and I was told, okay, now wash your hands there. And then I washed, and then that temperature gun, I don't know what it's called. He did it, he pointed it at me, and then he showed me, you're 38. So I looked at him. Okay, and I walked in. And he allowed me to walk in at 38. So That is a very, very big gap, my friend. You could walk into a supermarket with all these measures, washing hands and everything, but actually there is someone who literally has corona with you guys. So, guys, you have to stay safe, man. It is your responsibility. It reminds me of those days when Al-Shabaab used to attack us. They hear, but they tell you, okay, enter too. Yeah. So, guys, that was on a lighter note. We have to really take care of ourselves. Okay, back to the class. Density plots. It's more or less the same as histogram, but with a smooth shape. Yeah. So histogram has a way of including some noise. Density plots remove that noise. So with time, you'll get to understand noise in the context of data. But now just understand that the density plots, it's more of a smooth. I think we will have a session where we go through derivation of probability density plot, and you'll see how it transforms slowly from a histogram to a probability density plot. So I think we will cover that, and it will make much more sense. And my prayer is by the time you're covering that, I have a whiteboard where I can actually draw. Drawing stuff with Zoom whiteboard is really difficult. I want the natural way. Unahema kuchora na mouse. Unless I get the angle that nachora hivi and it projects. So maybe one day we'll get there. But the point where I'm driving, I really need to make it easier for you guys to understand. And such tools make it much, much easier for you to understand. And like just seeing a screen and then imagining that the density plot is removing noise. So you'll be wondering,
and what is this noise?
And what is this noise? Yeah. So some of these tools will help. Okay. All right. Before we move to the next slide, I want to invite questions. Paka pali tumefika. Any question? Yes, Silas? Oh, that is coming from Alvin.
Okay, I just wanted to, if I got it right, you said you're going to change it.
Sorry? What's your question, Edgar?
My question, actually, it's not a question. It's just to make sure that I think I got it right. You say going to change it. The inner fence, back to the outlier detection. Okay. Yeah.
Yeah.
The inner fence is basically the mild. It's just the same thing.
Yes. I need to replace. I need to change the name of inner fence.
No. You don't need to change. It's just an inner fence. An inner fence is the same as the mild outlier.
Yes. But the fences is equivalent to boundaries. So this value here becomes the inner fence. This one here becomes the outer fence. So
which one?
19 becomes the outer fence, basically the outer boundary, and then the -5 becomes the inner fence, which is the inner boundary. Look at them like lower boundary and upper boundary. So this one, for the sake of, because I cannot use the same term here and the same term here, it will confuse. I'll just rename these two mild outliers, and this one is strong outlier. So this one remains the inner fence and the outer fence. Make sense, or I've made you even more confused?
It's making more confused because if I go with see the rules.
Yeah.
If I remember the rules up there.
Yes.
Say that when you add 3 times the interquartile range to the third quartile, any number greater than this is a strong outlier.
Yes.
If you subtract 3 times the IQR to the first quartile, any number less than this is a strong outlier.
It's a suspected mild outlier. Yes, you're right.
it's any less than this is a strong outlier according to
yes, it's a strong outlier. Yes, 3. If you multiply 3.
Yeah, and all those, one will give you negative 14 and one will give you positive 28.
Value. Yes.
Yeah, 28.
Yes.
And they're all strong outliers.
Yes, exactly.
So
this one,
if that's the case, then outer fence is the same as the strong outlier.
Yes, you're right.
So you don't need to change the wording, just need to add. So we won't say that 14. We won't say that 14 is an inner fence. It's an inner fence. It's a strong outlier.
Yes.
Or outer fence. Yeah.
I think you've gotten the concept right. So I'll just need to add their strong outlier and mild outliers.
Yeah, because so that anything that we do with 1.5 is a mild outlier. Whether you add or subtract, it gives you a mild outlier.
Yes, absolutely.
Okay. Yeah. Okay, that was where I was trying to get confused.
All right, it's good that it's clarified now.
Okay.
All right. Any question or addition or? Alvin, are you still following?
Yes, I am.
Okay, good. Devi, are we together? Ama ulienda ukatafuta chai?
Tuko pamoja kabisa.
Ayub.
Yes, Robin.
Okay, I have a question. So you, at some point you mentioned that at times you deal with data that has got about millions of records. So in such cases, will, like, for example, Python, is it able now to just automatically identify for you the outliers, or you have to specify rules for it to identify the outliers?
There are 2 ways. There are 2 ways you can actually use to detect outliers. This one I've just explained to you one. And in a Jupyter notebook, you'll see a Python function that helps you detect these outliers, and you can actually remove them from the data. So using Python, you can actually implement this and write a function that would extract the outliers. There's another way that is called the Z-score. That one uses standard deviation. You can also use that to detect outliers. I'll mention it here briefly in the subsequent slides. Does that answer your question, Robin?
Yes, it does.
Okay. And you see the beauty is some of these things is we're just learning them manually to get the gist and understanding. Some of these things we have either existing functions or even existing libraries that does almost everything for us. So it is simplified. But the walkthrough is just for the sake of us guys to understand the workings of some of these, or rather things that sound or look complex. Okay. So I think let me handle this. We've spoken about skewness, kurtosis, suspend variable. We still have quite some slides. Probability, random variable. Wow. Okay. We still have quite a lot. All right. I think we can take a break at around 11. We take like a 10-minute break, and then we resume. We take 15 minutes break, and then we resume at 11:15. But before we do that, let me try and cover some additional slides. So what you're looking at is what we've generally explained, and I want to rather relate how I want to introduce a certain rule that governs a lot of statistics, especially hypothesis testing, which we will cover later in later classes in depth. So we normally have this statistical rule, 68, 95, 99.7 rule. Remember the example that I gave on our class and our ages?
Yeah.
The normal distribution. So
Yes.
when it is normal, basically our understanding is where does a normal distribution is under the assumption that majority of a certain sample, or rather a certain population, they normally tend to hang around the mean. Yeah. And few guys are normally outside towards the end. So if we take, for instance, either in a school or education sector or in a corporate where you have employees. Let's start with employees. Not everyone earns the same. Yeah, we might find other people earning more than others. We might find other people earning less than others. So if we get a situation, but most of the guys are normally average in the mean. So you look at a company X, and then someone tells you in company X, the average earning is say 100,000 shillings. Yeah? So when you go there, you might, based on your skills and experience, you might fall either less than 100 or above 100. But majority of the guys will be 100, hanging around 100, 120, 130, 80, 70. That is close to 100. Meaning, if you just perform, you'll get to 100, or in the next 2 years, you'll get to 100. And if you don't perform well, you might be kicked out, or if there is any restructuring or a salary pay cut, you can get from 120 to 100. Yeah. So most employees hang around, say 100K. But it does not mean that you don't have someone earning 500 in that company. The CEO might be earning 500,000 shillings. And it does not mean you don't have people earning 10,000 shillings, or even 20,000 shillings, or even 5,000 shillings, you know. So the fact that that is the reality, there need to be a way that that reality is reflected in our study. And the study is, when we are doing our descriptive statistics, we need to understand that majority of a sample or a population will always hang around the mean, but there is a possibility of having either less extreme end to the left or extreme end to the right. Now, again, I want to bring the concept of machine learning. What is the impact of that kind of distribution to your machine learning? Yeah. And what would happen if actually in a company you find that majority of people are earning less than the mean? For instance, we have a mean of 100,000, but you realize that, hey, okay, based on this distribution, majority of the guys are earning between 10 and say 30 or 40,000, or even 60,000. Majority of the guys. So if there are 10 people, you say seven people are earning less than 100,000, and then we have 2 people earning more. Okay, if you calculate, you'll get a different mean. But I just want to pass the concept where you have a mean value, but majority of the guys are earning less than, and we've already covered skewness. That would be will it be a positive skewed or a negative skewed?
A negative skewed.
Okay, yeah. So you get majority of the guys are earning less. So you need to understand what is the impact of that kind of distribution to your model and your predictions. Yeah. We dropped the bill. Let me just add him back. Okay. So what is the impact of that distribution to your data? Now there is a rule, 68, 95, and 99.7 rule. So basically, what this means is how many standard deviation further away from the mean is your data. Yeah. So the first rule, 68.27, it is 2 standard deviations away from the mean. 95.45 is 3 standard deviations away from the mean. And then 99.73 is 3 standard deviation away from the mean. 95.45 is 2 standard deviation away from the mean, and 68.27 is 1 standard deviation away from the mean. So basically, this is the rule governing how many deviations away from the mean is our data point. So this study is going to be very, very significant when we start, this rule rather, is going to be very, very significant when we start learning about hypothesis testing, where we will have the null hypothesis and level of significance, the confidence interval will anchor a lot on this rule. and we will mention our confidence interval or confidence level to be either, we'll use one of these, 95.45 or 95%, yeah, 68.27. We'll use one of these to make our conclusion, yeah. So the relationship between a normal distribution and a box plot is visually probability density function. You're looking at it below there. If we were to compare that with a box plot, and based on the rule, majority of data is within first deviation away from the mean, and we have other data points falling second and third deviation away from the mean. Now, my question to you guys: if this thing is way from, you know, we have third deviation, fourth, fifth deviation from the mean. So if it falls outside the third deviation from the mean visually, what would you call that? We've already covered it. Anyone? The first guy to give it a shot? Just look at the box plot and look at the probability density function. If that value goes away from the third deviation away from the mean, what do we call it? It's an open book question. Huh? Good people. Can you guys see the slide?
Yes.
Is the question clear? I'm just confirming. Is the question understood? Edgar, I feel like you have something to say. Just say it.
Now I'm just trying to get to understand what it means by one standard deviation away from the mean, second away from the mean using the rule. Okay. So that I can answer it, yeah. Because I haven't yet understood what it's really mean.
Okay, let me say there is a way you can get the standard deviation of a certain data set.
Yeah.
So when you get the standard deviation, basically the standard deviation, it tells you it gives you some information about the variance that data point is from in comparison to the entire data set. It's it explains some variance of that specific data point within the context of that data set. So to make it completely simple, assume, let's look at the first plot, 68, 95, and 99.7 rule. That plot. You guys can see where the mean is. The mean is right at this one here. Yeah. So what this means, standard deviation from the mean, it's like the variance or the distance. Let me just use a different terminology, because if you make reference to let's go back to this where I had explained we get buckets. We get buckets, yeah. We have the first bucket here, the second bucket here, the third bucket here, yeah. So we have the first bucket containing 4, 3, 2, 1. We have 4 people in the first bucket, or rather, let's take 5. We have 5 people in the first bucket. So the question I'm asking is, how many? How far is this bucket? How far is this bucket from here? This is the mean. You get? How far is this bucket? Remember, there is a difference between how far is this bucket and how far is this data point. So there is this bucket where we have few guys. How far is this bucket from the mean? And how far is this bucket from the mean? So if we have several buckets, yeah, that is what we are calling about standard deviation away from the mean. Yeah. So it says that majority of data will always fall within the mean, like first 1 standard deviation away from the mean. That is the 60. Let's go back. Yeah.
All right.
68.27. You get? So it's saying majority. Remember this boundary, upper and upper.
Yeah.
So majority of the data will fall here, but we have others that are falling 95 point. Okay, like now, let's explain it the other way. Yeah, almost everyone will fall 3 standard deviation away from the mean. Yes.
Yes.
Almost everyone will fall 3 standard deviation away from the mean, which is 99.73. It makes sense. 99.73 of a population is almost everyone. But we also have the second band where we have 2 standard deviation away from the mean. We have another set of groups, yeah, that needs to be studied separately. You get? So this 95.45 takes care of the study is different. Yeah, and the study is based on 95.45. You can choose to study this 95.45. Yeah, you take a population and study the 95.45, or others could choose to study the 99.73. Yeah, and others could choose to study the 68.27. 68.27. So each of these studies, using central limit theorem, the difference of the inference should be negligible. It shouldn't be statistically significant to come up with a different conclusion. You understand? So if I do a study with 95.45 and someone else does the same study with 99.73, the difference between our studies should more or less come up with the same conclusion, regardless of. But we studied we did the same study, but different population. So when population from the mean, that is exactly what it means.
Okay.
Now I ask the question now. If we have values outside the third standard deviation away from the mean, what do we call them? Iko hapa. Angalia hii box plot. Angalia here. So basically what I'm asking is, what is this?
The outliers.
Absolutely.
The outliers.
Yes. That is what I wanted to talk about. And here it is. Yeah. You see this color is the same as this color. Yeah. So depending on there are certain studies that we will do when we are talking about kurtosis. Those are the next slides. We're talking about the kurtosis. We're talking about actually kurtosis. It has a relation to that.
Okay.
Before we go for break, anyone with a question? Anyone with a question? Okay, then I think we can take a break. When we resume, in the next 15 minutes, we can resume at 22.
11:20.
11:20. 11:22. Okay, so let's resume at 11:22, and we will proceed. Okay. So I'm assuming you guys can see the slide.
Yes, we can see it.
Perfect. Okay. All right. So we had reached the box plot probability density function. Excuse me. So based on based on the slide, I have spoken about skewness, and now we're going to talk about kurtosis. So we have several, actually three. These are complex terms, but ideally, with time, they're going to make much more sense. So the first one, it's a normal. It's a normal. Okay, let me start with the ones that are different. We have leptokurtic distribution and mesokurtic distribution. So when you talk about kurtosis, it has something to do with the size of the tail. And of particular interest is when you're looking at the tail of a distribution. On the previous slide, I showed you guys the tail where you can map it to a box plot and actually get to see how the outliers fit. And I would like to use that as an example of explaining kurtosis and in particular mesokurtic or platykurtic. Now, if you look at, let me see the next slide. Did I have it here? All right. Okay. Yeah. Look at the slide of the first plot that has a red line. We have another one that has a black line, and we have another one that has a green line. Yeah. Now, this is not probably going to be the best slide to explain this. Let me pull the best image. Let me pull the image in a few. Give me a few minutes. I'm just going to pull in a notebook that I had done previously. It will become much more clear. Just give me a minute. Okay, if there isn't any question, I think we'll move to now there is clear understanding of kurtosis, skewness, and I was using this to I've explained this on spend. If in case you have like for example in class we were working with looking at the distribution of spend, how much people spend with time, and if you map a normal distribution and against the actual distribution, then you'll see the actual distribution. We have thicker tails, and it means that even in less likelihood time windows, you collecting some money is possible. Look at the values: 1,250, 1,500, 1,750. Yeah. So these are values that lie beyond the 3 standard deviation away from the mean. So the likelihood of them actually happening exists. So you really wouldn't destock item that is say 200,000 because the possibility of it happening exists. So if that television was 1,250 or that one item, or we have spenders, if we have spenders, if you have people shopping after 8 p.m., then you wouldn't close your shop because the likelihood of someone coming and spending more than 1,000 is there. So depending on what you're studying, depending on what your data is telling you, it is important to have such interpretation. A good case in point is it could be even such things normally advise things like is a business at risk? Should I invest in this business or not? What time should I be opening my branches? What measures of security measures or mitigation measures should I take? These are informed by looking at the data within a certain period and coming up and understanding the kurtosis of that data. So the kurtosis is not just a descriptive measure that you do it and then you move on. You need to be able to interpret and understand what is the impact and what inference can you derive out of the kurtosis you get from your data set. Okay. All right. Heteroscedasticity and homoscedasticity are the other concepts that you need to understand. And it is largely based on the assumptions of linear regression. So the assumption of linear regression, one of the assumptions of linear regression is the residuals need to be homoscedastic, meaning they need to be variants. They need to be the same. But if you see that the residual, the standard error is not the same, and it's showing a certain, if you were to plot the scatter plot of standard errors, and you observe a pattern like what is displayed on the PowerPoint slide, then it's said to be heteroscedastic. So heteroscedastic means that as the values increase, the errors increase, the standard error increases. And the assumption is as the values increase, the standard error should be the same. So that assumption is not complied to. And you probably want to use either other regression models, or you'd want to either fix this through the techniques that are available. So a homoscedastic distribution is one that it is standard. So what you observe there, instead of a cone, you look at it like it's straight line. So it is standard across from the beginning to the end. It's not a cone. So that is what homoscedastic and heteroscedastic come to be. You can detect this, and there are other plots that you can plot to be able to determine this. One of them is ggplot. We are going to cover quite a lot of this in subsequent classes. Probability. Wow, this statistics class is more theoretical. A lot of theoretical. I hope I'm not losing you guys.
But enjoyable.
I hope it is. I hope it is.
Yeah, it's really.
Yeah.
It's really enjoyable.
That's
not
good.
Getting to understand the hetero.
Yeah, with time utakuwa unaiongelea kama ni kijaluo.
Heteros. Okay. Whatever it is.
But
we'll get used to it. Yeah, we'll pronounce it, we'll get used to it.
Yes, yeah. Yes. Davey, are we together? I think we dropped some people along the way because of the bundles issue. Davey?
Yes, I'm still here.
Okay, perfect. All right. Conditional probability. Now I'm going to take a bit of a laid-back approach, and you guys, it's going to be an engagement. Some of this probability task we were taught, and contrary to what we've covered so far, I think this is the most straightforward. I would like to hear what you guys have to say about probability, especially conditional probability. David, able to unmute?
I think it's the probability of something happening based on a condition being fulfilled.
Yes. Yes. Absolutely. So an event happens, and then based on that event, what is the probability of a subsequent event happening? Yeah. So there are some exercises there. I think we did this in class, and I'm not so sure we'll cover what we wanted to cover in this. For the sake of time, I think I'll just move to the next one. You could replay this recording and come to this slide and try and do that exercise.
What are the answers of the exercise?
If I tell you the answers now, you won't try. Have your own answers and then reach out to me. I'll give you the answers. That is better.
The question?
Suppose that somebody secretly rolls 2 fair 6-sided dice. Let the 1 be the value rolled on die 1 and the 2 be the value rolled on die 2. The first question is, what is the probability that the 1 equals to 2? What is the probability that the 1 plus the 2 is less than or equal to 5? What is the probability that d equals to 1, given that the 1 plus the 2 is less than or equal to 5? I can give you a tip on how to approach it. Use Excel sheets. Put the 1 and the 2 as the 1 values to be on the in columns, and then the 2 values to be in columns, the 1 values to be in the row, and then try and map out. You'll get the answers to all the 3 questions. You could have your own approach, but it's a pretty straightforward exercise. So come back to this slide, try out this exercise, and once you get your answers, reach out to me. Okay?
Okay.
All right. The independence, when you're explaining probability, there's probability independence. Anyone who wants to give this a shot? Dino?
It's that the occurrence of one event is not or does not affect the occurrence of another event.
Absolutely.
Yeah, yes.
Absolutely. So it's an example is flipping a die and flipping a coin. You getting a 6 the top of a die does not have an impact, or it does not affect you getting a head or a tail. Those two are mutually exclusive.
Independent.
All right? Conditional independence. Who wants to take that a shot? Dan, karibu sana, and I'm going to welcome you in that question. Try and explain to us conditional independence. Dan, nimekuseti. So in simple English, conditional independence is this independence is observed for as long as a third event has not occurred. But the moment it occurs, the outcome could be influenced. The outcome could be influenced. The independence is no longer exists. So that is what this means in layman language. Okay. All right. Random experiment. I want to pose the same question to, I don't know if Dan is on. Okay, as we wait for Dan, Robin, What do you understand by a random experiment?
I think that's from the slide. It's something that once you do, you don't have a certain outcome. So you're just doing an experiment without any certainty. You can't predict that it's going to be outcome A or outcome B.
Absolutely. A random experiment is one which the outcome you can never know. It can go either way. For example, tossing a coin, that is random. Tossing a coin, the first event when you toss, the first outcome could be a head, but you cannot tell if the next one is going to be a tail. Yeah, you cannot tell if the subsequent one is going to be a head or a tail. Each and every single time you toss it, the outcome is unknown until you collect the observation. So that is a random experiment. And a random variable is the variable that stores the outcome of the experiment. So a random variable also, you wouldn't know the value it's going to contain. So if you put a variable like x is the number of heads and y is the number of tails, then during the experiment, you wouldn't know the values that are going to be contained in those variables. So that is why we call them random variables. Now, we have discrete and continuous random variables. For instance, head or tail, that is a discrete random variable. Yeah, it can either be head or tail. It can't take
half tail.
Sorry?
It can't be half head, half tail.
Yes, exactly. Exactly. It is discrete. Yeah. Now, but when we are looking at things like those guys who like nyamachoma, it is continuous. You cannot get an absolute. You can get 3.4 kg, 3.45 kg, 3.45, 6, 7, 8, 9 kgs, depending on your artillery, it was, yeah, the measure. The precision of the measure. If the machine you're using is to 2 decimal places, you can get 3.45, 2.18. So ukienda unasema nipatie nyama ya 2 kilograms. Utaona 2.00 ama utaona 2.01 alafu nakupatia hata kuongeza bei. So that is an example of random variable that is continuous. Depending on the experiment that you're doing, then it can either be you'll either be storing discrete values, or you can either be storing random values. All right. Now that brings us to what you're calling the sample space. When you're doing an experiment, what are the possible outcomes? What are all the possible outcomes? All the possible outcomes. If you are to record your experiment, what are all the possible outcomes? Now, all the possible outcomes become your sample space. And from within the sample space, you'll see now how we derive calculations of probability, the probability of getting a specific outcome within the sample space. So you'll be asking yourself questions like, what are the probability of getting head-head if you toss a coin 10 times? Yeah. What is the probability of getting a head-tail if you toss a coin 10 times? Or to make it simpler, tossing a coin 3 times. What is the probability of getting all of the toss heads, or all of the tosses tails, or head, tail? Yeah. So we first need to understand what is our sample space, and then we derive or calculate the probability. And I just gave you an explanation, and that is what you're looking at in the slide. Assuming we have random variable x, which is the number of heads after 3 flips of a fair coin. What is the probability of x equals to 0? Meaning, we won't get heads. So we are storing the number of heads into a random variable called x. So if x is 0, means that we won't get any head. So we need to first find what is our sample space. Once we find our sample space, then we calculate, or we rather determine which of the outcomes are we interested in. And we're interested in outcomes that do not have a head. So let's look at the slide. So sample space, we have 8. How did we come up with this 8? So if I test a coin 3 times, the first outcome, it could be a head, head, head. The first flip, head. The second flip, head. The third flip, head. Now, that is the first event, head, head, head. The second one, it could be a head, head, tail. The third one, it could be a head, tail, head. The fourth one, head, tail, tail.
Tail.
Fifth, tail, head, head. The sixth, tail, head, tail. The seventh, tail, tail, head. And the last one, tail, tail, tail. Nigani that aiko kwa sample space. Let's take some thought over there. Let's all just look at the slide and then think through which one is missing. Which one is missing from the sample space? I want us to all understand how we derive the sample space. And Silas, are we together? Silas? Okay. Who feels that there is an observation that we have not recorded? Okay. If there isn't none, I'll assume that we've captured all the observations and we move on. So what is our interest? We want to check the probability that the outcome has no head. Yeah, we've identified our sample space is 8. What is the probability that we won't get?
1 over 8.
1 over 8. Okay?
Yeah.
So that is 1 over 8. All right. We've identified the sample space and we've checked that our interest is where we have no head. Okay.
Yeah.
What is the probability of getting 1 head? Exactly 1 head.
1 head.
Yeah. In the observation.
Three over 8.
Absolutely. 3 over 8.
Yeah. 3 over 8.
Okay, I'm going to take a pause over there. How many guys are lost? How many guys are following? How many guys are just moving on?
Following.
They know you're following? Okay, that's good. Alvin?
Following.
Alvin, you're following?
Yes, yes.
Good. Davy? Did we lose Davy or? All right. All right. Okay. Now that is how you calculate the probability, and in this case, it is a discrete probability. So remember how we built our probability in reference to the probability density factor. Yeah. So let's look at this observation. And if we were to plot this observation, what is the probability of getting a 0? We get it's an 1/8. The event is, what is the probability of having no head in that event, which is 0? The probability is an 1/8. I hope you guys can see. This is very, very crucial. So I'm really hoping that you guys are following. And then the second one is, what is the probability of getting only 1 head in the observation? So getting only 1 head in the observation, it could be Head, tail, tail.
Head, tail, tail.
Tail, head,
Tail, head, tail. Tail, tail,
Tail,
head.
tail, tail.
Yes, tail, tail, head.
Yeah.
Yes, exactly. So that one, it is, and we've seen that the probability is 3/8.
Yeah.
And then we look at what is the probability of getting 2 heads.
2 heads.
So we
Head,
count
head,
again.
tail. Head, head, tail. Head, tail, head. And tail, head, head.
Perfect.
So that's 3/8.
Yes, exactly. So the probability is 3/8. So when you plot that from the slide, you can actually see 1 and 2 have 3/8 probability. And then we look at what is the probability of getting all of them head.
Ahead.
Yes.
1/8.
Yes.
1/8, yeah.
Yes. So you look at this probability density function. If you plot it, it will actually see it is a normal distribution. And this is a random experiment. This is a random experiment. And when we plot the probabilities, we actually see that it is normally distributed. If you are to draw from the center of each, if you are to draw a probability, a PDF, a probability density function, this one gives you a histogram. But what is the probability density function? If you take a line and you draw it straight, passing through the middle, it will come to the middle of that, and then comes down, and then comes there. Normal distribution. And looking at the 68, 95, 97 rule, statistical rule, it will tell you majority of the data normally tends towards the mean. Now let's look at the probabilities. The probability 3/8 and 1/8, which one is bigger? Three over 8 and 1/8, which one is bigger?
3/8.
Yes, 3/8. So majority, the probability of you getting, the probability, what this means is the probability of you getting a 1, at least a head or a tail, is high. True or false?
True.
The probability of you getting a head, at least a head or a tail, is high than the others. And if you look at this probability density, it shows you it is falling within 68 point. The event being getting a head or a tail. But if the event of you not getting, a head, meaning in all your tossing, you only get tails, is 1/8, which is less. So the probability of you observing that, as much as it is likely, but the probability is less. So with that concept in mind, we can move to the next slide. I hope it's making sense now.
Yeah.
All right. So we can look at now another experiment where since our data set is a shopping data set, let's look at if you were to just walk into, say, Tuskys and observe the number of people queuing on a specific teller between 4 p.m. or at exactly 4 p.m. You go to Tuskys, you pick one branch, and you go to that branch every single day for the next, say, 500 visits. Yeah. When corona iko hakuna kazi unafanya, kazi yako ni kuhesabu watu wako kwa queue. So let's assume you've created your job and now kazi yako ni 4 p.m. exactly, unaenda kwa super and you want to see how many guys are queuing or on a specific teller. And that teller could be either your girlfriend or your wife or your husband, depending on now why you would want to count all those things for your own personal reason. Now, back to class. On day 1, you see now anabangaiza tu hakuna queue. 4 p.m. exactly. Unaona hakuna queue on day 1. And then on day 6, you do it randomly and you figure out out of all those 500 visits, you've seen that 24 times at exactly 4 p.m. wherever you are, that teller is alikuwa anapangaiza tu. And then 18 times kulikuwa na mtu mmoja, and 8 times kulikuwa na watu wawili.
Watu wawili.
Yeah. So let's assume it's actually 50, not 500 times. So it's actually 50. Now, what is the probability estimate of you finding line size 0? Like hakuna mtu. What is the probability? So that, let me say ni mtu mmoja kubonga naye. So what is the probability that kesho ukienda either atakuwa na mtu, ama atakuwa na mtu mmoja, ama atakuwa na watu wawili? That is the question. So if you look at the probability estimate, the probability of her not having or him not having anyone in the queue is 24 out of
50,
which is 48%. So there is 48% likelihood that there will be no one when you go there tomorrow. That is what that slide means. Okay, continuous probability distribution. Before we proceed, I want to ask a question, and the question is posed right there. What is the area of a line? Do you know?
Area of the line.
Yes, what is the area of a line?
I'm not sure, but with my basic maths, you use the height time you multiply by the length and
Okay.
the mathematics.
Okay,
Yes.
so what is the, let's start from the ground now. A line can have a length. So now you draw a horizontal line. It will have a length, yes?
Yes.
But what is the width?
The thickness?
Width, the width. See, area is equal to length times width.
Yes.
So what is the width of a line?
It's 0.
Let me give you a tip. On the line, you're plotting the line in a Cartesian plane, and the line is thin. How would you measure it? What would be the width of that line? If you draw a horizontal line or a vertical line in a Cartesian plane, just a line, what will be the width?
It will be 0.
Length.
Okay. Okay. I'm getting very good answers. It will be something tending towards 0.
Yeah.
It will be something very, very, very small.
Yeah.
Sorry? Okay. Yeah, so it will be something very, very small. Now, with that in mind, let's start walking this journey. Yeah. Let's draw a horizontal line. And we have a continuous random variable x. And we looked at the probability of getting ahead to be 1/8. 1/8. Let's see that. Or let's put the previous example. Let's put it aside, and let's use a completely new example. So let's draw a horizontal line, and we draw it on with a height of 1/5 on the Cartesian plane. This height here. So this line. Yeah. And then, so the height of this line is this, and the width is from 0 all the way to 5. We ask ourselves, the probability of getting a value here. What will be the probability of getting a value of, say, x value of 0.5? Let me rephrase the question. Let me rephrase the question. What is
nasema this is Alvin kutoka Lexaco. Jana tutafutia swala kupata.
Alvin, I can't even mute you. I've muted him. Okay.
Oh, okay. So what nilikuwa naulizia ni tulikuwa na.
All right. That was yeah, that is Alvin. Yeah. Okay. If x, let's start from here. X is a value that is less than or equal to, x is a value that is greater than or equal to 1, but less than or equal to 2.
2.
So we are talking about this region here. So getting an x value between 1 and 2. So if you were to take the area of this region, it will be, what is the difference between this? This will be 2 minus 1, which is 1, times the height, which is 1 times 1 over 5.
5, yeah.
So the area will be 1 over 5.
1 over 5.
Let's take another value of this area. X is between 2.9, this yellow here. So we pick a point here, 2.9.
Come up again, Ayub.
Sorry?
Come up again. I didn't get you. X is between.
Now we take this color here. X is between 2.9, which is close to 3.
Yeah, 2.9.
Yeah, 2.9 and 3.1. What would be the area of this curve, of this region? It will be 1 over 5 times, which is the length, which is the height, times this distance here. So the distance we get it from deducting 3.1 from 2.9.
2.9.
Yes. So 3.1 minus 2.9, you get the distance. So it will be.
That is.
Do that math.
0.
Is it not going to be 0.1? No, 3.1 minus 2.9 is 0.2.
0.2. Yeah, 0.2 times 1.5. Plus, yeah.
Yeah, so 0.2 times 1.5, what do you get?
0.3.
Able to convert into fractions. 1 over 5, what is 0.2? 0.2 C is equals to 2 over 10.
1 over 3.
No. 0.2 is equals to 2 over 10.
Yes.
So 2 over 10 simplified, it becomes
1 over 5.
1 over 5.
1 over 5, yeah.
It becomes 1 over 5. So
1 over 5
times 1 over 5, you get 1 over 25.
1 over 25, yes.
Yeah. So let's observe if the area.
Get 1 over 5.
Yes, exactly. So if the area is bigger, it means the denominator is bigger. But as we move towards a smaller area, we want to come to as close as possible to a specific point. The denominator becomes bigger. True or false?
Pardon?
I want you guys to walk through this because it's the entry of it's the beginning of transitioning into discrete values, into continuous values, doing probability density of continuous values. The first one here, we had discrete values. Yeah, this is discrete probability. Yeah, and we need to understand how we derive probability density function of continuous values, because in real life most of the values are continuous. Now let's start from, let's say we want to get a point in the x-axis, and this point is between x greater than 1, greater or equal to 1, but it is less or equal to 2.
2.
What is the area? We've calculated the area is 1/5, because area is length, height times width. The height is 1/5, the width is 1.
1, yeah.
Yeah. So let's move to this one, the yellow one. The yellow one, what we are looking at a smaller area. So we choose arbitrarily. Arbitrarily, we are choosing a value of x that is greater than or equal to 4 here, and it is less than or equal to 4 1/3. Yeah. So this is a value on the x-axis. You see, these are arbitrary values, yeah, that we can pick from the x-axis. So in fractional terms, it is 1/3 times 1/5. So this 1/3, excuse me. If you take this difference, 4 1/3 minus 4. So this one is 4 1/3 minus 4. You will get 1/3. The distance between here and here, it is 1/3. And the distance between here and here is 1/5. So getting the area becomes 1/15. So look at it visually. This area, 1/15, the area of 1/15 is smaller than the area of 1/5, this one. Yeah. Now, if we make even smaller, we are like moving into a precise spot on the x-axis. Remember, we were choosing a value between 1 and 2. Yeah, x value between 1 and 2. Now we have made it smaller. We're only interested in a value between 4 and 1/3. And we are now moving it even much smaller. We are looking at a value between 2.9 and 3.1 in the x-axis. So if you get a value between 2.9 and 3.1, yeah, that distance is 1/5, and the height is 1/5. So the area of that value becomes 1/25. So as you move closer and closer and closer to a single spot, yeah, it means the probability of, okay, sorry, before I introduce the probability, it means the area of that, spot is smaller and smaller. Yeah. So if in terms of probability, for example, if we are looking at this value here, 2.9 and 3.1, it is 1/5 times 1/5, which is 1/25. If we look at even more precision, 3.01, it changes to 1/250. Now, what we're observing is the area has a way of telling us the probability of finding a a point. For example, the chances of getting a point between 1 and 2 on the x-axis, we've seen is 1 over 5. The probability of getting between this and this, is as per the slide. So the take home here is continuous random variables, probabilities. That is how you translate from, that is the understanding you translate from discrete to continuous. You're trying to move to identify the probability of a value like 2.001 because it exists in the Cartesian plane. I don't know, does it make sense?
It does.
Do you know?
Barely, but I'm following.
What is the gray area? What is the question? Or rather, what is not clear?
You see, if we are subtracting 2 points from, let's say, for example, if I can use the one with 2.9, 2.9 less than 3.1. Unaona hiyo part?
Yes, yes.
See, hapo we get 0.2, right? No.
Yes.
Yeah, 0.2.
Yes.
Is 1.5. Hiyo 1.5 ingine tuna multiply nayo ni the length of the line.
Yes.
And
the length of
that's
the, yes.
The height the value of the y-axis kwa line aliko.
Oh, the value of the y-axis.
Until there, because umenishika hapo.
Yes, yes, nimekushika.
So if I get 125, what is that value?
That value is the probability of getting that point. So you see all these points, 1, 2, 3, 4, 5. Let's assume they all have the same probability of being picked. You take if you take 5 balls and put them into a box, and each of those balls are labeled 1, 2, 3, 4, and 5. What is the probability of picking ball number 3? What will it be? Tell me.
3 over 5. 3 over 5.
No.
1 over 5.
Ball number 3.
1 over 5. I mean.
Yes, absolutely.
1 over 5.
Absolutely. So what will be the probability of picking the ball number 1?
It's still 1 over 5.
Absolutely. So all those balls, the probability of picking each one of them is uniform. Yeah. So if the y-axis reflects the probability of picking the balls, now let's think that this 1, 2, 3, 4, 5 are actually not balls, but they are discrete values. It could contain, sorry, not discrete, continuous. You could actually go and fetch 1.2.
Continuous values.
Yes, continuous values. You could go and fetch 1.2, 1.8, 2.9. So we want to transition from discrete probabilities to continuous probabilities. And through continuous probability, we derive the probability density function. And that is why previously I had explained with a histogram. A histogram gives you probabilities of discrete values. A probability density function, it gives you, there is a way you can map a histogram into a PDF. But probability density function, it gives you the same, but now of continuous values. So with that understanding, if we had continuous values like right now, 2.9 and 3.1, what is the probability of getting a value between 2.9 and 3.1? So when you get a value of 1 over 25, that is the probability of getting that value. If you have a value that is less than or equal to 3.1, but it is greater than or equal to 2.9, what would that probability be? Because right now it is now continuous. So the value you're seeing, 1 over 25, is the probability of getting that continuous or any value there between 2.9. So if we say, what is the probability of getting 3? Because 3 is between 2.9 and 3.1. Yeah?
Tumeelewana.
Tumeelewana?
Yes.
Okay, perfect. All right. Any other question? Alvin, are we together?
Yes, we are.
All right, that's good. Devi, I lost you. I don't know if you're back.
Yeah, I'm back na nimeelewa.
Umeelewa? Wakati hapo ulikuwa MIA. Good to have you back. Umeelewa?
Kabisa.
Okay, sawa. Mimi nachungulia tu. Ukipotea, I will know. Unajua Zoom iko na matrix. Mtu anaweza login Zoom na endelee kupika githeri. So sisi tunaendelea na class na githeri naiva. Sasa shida ni githeri kishaiva sisi hatukuli. Alafu wewe baadaye utakula githeri, alafu baadaye unakula tena class kwa sababu class iko recorded.
Nikuje tu nione.
Sawa. Good to have you back.
Okay.
Let's go to the next one. Now, this slide here inaonyesha the assignments that we had agreed we will do for the first week. Where through Jupyter Notebook, you use the data set to do your own descriptive statistics and then infer. Yeah. So there were some topics that were not covered, but if you can study them and generate your own questions, we are going to cover them in the next class. Things like hypothesis testing, we have not covered those, but we are definitely going to cover them. So inferential statistics bit is something that you can choose to try or not to try. But the descriptive statistics, try and from the data set, if you don't have it, I'm going to share the data set and sample Jupyter Notebook. So you guys can actually try and do this. Most of you guys have done them. So I think it's, I'm not so sure if Alvin has done this and any other guy who's new, but this was the exercise that was given after the first statistics class. And the next thing was hands-on practical sessions where we look at the Jupyter Notebook. I'm going to open it and then we walk through it. And then when I share the notebook, you can actually type. Let me see the next class. Yeah, we will cover null hypothesis. We'll cover alternate hypothesis, writing hypothesis testing, statistical definitions. Statistical tests, Z-score, p-values, statistical error, and then we'll also touch on categorical data analysis, and then we do Jupyter Notebook. All right, so I think we pause there. Some of these things we will cover next week on Saturday. We will also cover them. I've mentioned them in this meeting, in this session, but we'll definitely cover them in coming Saturday. So let me open the Jupyter Notebook and then we walk through. I had actually opened it. We'll walk through that and then I'll share the Jupyter Notebook. So for that to happen, I'm going to stop sharing and then I open the Jupyter Notebook. Just give me a minute. Okay, can you guys see the Jupyter Notebook?
Yes.
Perfect. Is it visible? The small I can enlarge it.
It's visible.
It's visible.
Yeah.
All right. So all my notebooks normally have problem statements, and then I describe the data sets, and you could practice the same thing. The first cell is where you put the libraries you're going to use. All the libraries, there are quite a number of libraries. And let's see. Yes, Silas, I will definitely share the notebook, but the participation in class is also very, very important. It's not a matter of playing the recording and following the notebook. It is important. What I encourage in my sessions is participation in class, as well as asking questions and doing everything, because let's face the reality. Immediately after these 2 hours are done, you have the next thing you need to do. You have another thing you need to do. So most likely, just like all the other online tutorials, you will say, I will come back and read, but we hardly get that time. It is a fast pace, kama si shule ni kazi, kama si kazi. So the maximum you can benefit is for 100% participation in this 2 hour or 3 hour session. That is what I really, really encourage. But that is for those guys who are really serious and they want to really capitalize on learning this thing. And if you feel that you can still follow through by getting the notebooks and listening to the recording, then that's fine. People are different and people learn differently. And what I would really vouch for is for you guys to participate in class. After class, if you have a question and you don't know where to get the answer, you'll either reach out to your students, but when you reach out to me, I might not be responsive as you would wish because I'm engaged on other things, or yeah, so that is the reality. So don't worry, I will share the notebook and I will also have the recording available for those people who want to follow through. Okay, so the first notebook, you import your libraries, and then the second one is where now you import your data sets, yeah, into a data frame. And if your data set has dates, it's always good to pass those dates so that by the time you're importing it, it is already converted into date format. This is normally important, especially when you're doing either time series or you want to use date manipulation. So with pandas, you cannot use date manipulation if the column for date is not in date format. So if you import it without this, the date column would be imported as string, and you'll have a lot of problems. So the first thing you'll need to do is to just see the top. There are a couple of things you can do. You can just check out what are the top 5 values, what are the bottom 5 values, or you could random using sample. And if you want to check the bottom values, you use the tail command. So we've not started doing prediction yet. We did predictions in the first class, beginner. So these ones I'll just skim through. The objective of this one is just to check out the descriptive statistics. So how to check out the mean, that is the formula for checking out the mean, the median. So you pick a certain column and you want to check the distributive for specific columns. There is one way of measuring overall descriptive stats. I want to give you that as an assignment. Go and figure out if you want to check the descriptive statistics of an entire data frame, how would you go about it? It's a simple command, and it is not so far from the word descriptive statistics. So you go and figure out, and pole pole. I always like saying ujinga inatoka. Me, when I learn something from you guys, ujinga imetoka kwangu. So when you learn something new from me, ujinga imetoka kwako, and na pamoja tunatoa ujinga. So that is what my sessions is all about. We are fighting stupidity and ignorance. So stupidity and ignorance is one constant thing that will always be there. And the more you learn, the more you participate, you reduce the level. So the difference between the professionals who are really good in this thing and us guys, it's the stupidity is less. Their stupidity and ile threshold ya ujinga ile yao wako nayo ni kidogo kuliko yetu. Yetu ni kubwa. So tukisoma hii kitu ujinga ina reduce. So that is what we do in our class. Tunapunguza ujinga. Yes. So go and figure out that, and I can see from the chat session, people already have the answers. That is good. It's something very, very simple. And then we measure we have measures of spread. Yeah. So measures of centers, and we have measures of spread. I think this we covered in the previous classes. Measures of spread are things like the quantile. When you want to check the first quartile, the second quartile, or the things that we are talking about when we are speaking about interquartile range. This is how now you derive. So for example, if it was a salary, how do you get there? I think, Robin, you're the one who asked this question. How do you get the first quartile, the second quartile? This is how you get the quartile, and then from the values that you get, you can actually derive the interquartile range. So it's just deduction, like right now. If we were to get the spend interquartile range, you get the quartile 3 and quartile 1, you get your interquartile range. And then you want to plot a box plot and check out outliers. That is how you plot a box plot. Yeah, the library being used, you can use a dataframe.boxplot and pass parameters to grid. So the more you play around this, the better. And then if you want to check out the variance of that specific column, you use the word var. Yeah. If you want to check the standard deviation of that particular column, you get the 248. So if the standard deviation of spend is 248, how many standard deviation is it from the mean of a specific point? So that one is in relation to what we discussed previously. And then if you want to get the median, it's this very, very simple, straightforward. And the libraries do all this stuff for us, guys. Yeah. Okay. Measures of non-symmetry. Yeah. So we have skewness, where it is positive skewness, negative skewness. When it is positive skewed, the tail is tending towards the right. When it's negative skewed, the tail is tending towards the left. An understanding of this kind of distribution is if you have majority of guys in a class that are younger, then it's most likely to be a positive skewed. We use this example in when we are looking at the previous slides. And then getting the coefficients of skewness. Yeah. These are the coefficients of skewness. And then when you want to get skewness of all the rows, yeah, that is a function. And this keep a name just basically means if you find a null value, don't display the results. Yeah. And then the skew of an entire column, you check it out, it's 4. And then we come to kurtosis, description and understanding of the kurtosis. I said when the kurtosis is greater than 3, it is leptokurtic and the tail is fatter. When the kurtosis is less than 3, it is platykurtic and the tail is thinner. Yeah. Mesokurtic is a normal distribution, another name of a normal distribution. That is a graph. And for you to get kurtosis of a certain column, you just call the KURP, the spend kurtosis. You get it to be 20. Yeah. And then now this one you can best, if it is on spend and you want to map it against the normal distribution, that's what you get. The blue line is the normal distribution and the orange is at the actual values. So if you plot the distribution of the actual values, you have guys spending even way outside the standard deviation from the mean. Yeah. And if this one, look at where the mean is. Which kind of skewness is this? It's an open book. Which kind of skewness is this? Menda mute tena. I choose. It's an open book. You only just need
normal.
For the actual values, which skewness is in the actual values? When you look at this data, when you draw, look at the tip of each of these points. If you draw a line as compared to the normal distribution, Look at where the mean, most most values are falling this side. Robin?
Okay. What was the question, Ayub?
Which
I didn't get the question right.
Okay, which skewness is this in this plot?
Well, it's positive skewed.
Yes, it is. Jibu iko tu hapo mbele tu. Hata sijui watu walishindwa kusoma ama namna gani? Ama watu wanaona it's so obvious mpaka anasema let me just I know. All right, so this is positive skewed. So look at the tail. The tail is turning towards the right, yeah? And
Towards the right.
when you look at the mean, yes, exactly. All right. Heteroscedasticity, I'd say that you look at the pattern when you plot a scatter plot. Some of these things are not necessary for you to do. The reason why I visualize them is for you guys to understand the concept. But most of these algorithms are able to automatically pick these patterns and tell you whether your distribution is heteroscedastic or homoscedastic, right? Right. So that is more about it. I think the next are now the next functions, or rather the next cells, are for visualizing and doing predictions. So it was an incomplete notebook. So I won't go back. I won't go through this because those are just a code for you to help in understanding the visualization, which are key in telling a story. So as an ML engineer, you need to be good in telling stories using visuals. You need to be good in understanding your descriptive stats and what they mean and the impact or the possible correlation between what you see in your descriptive and the model outcome. So will you see a reflection of what you see in your model, and what will be the impact of what you see in your predictions? That is very, very crucial. Any questions? I think we are 2 minutes to end of time. It's amazing how 3 hours can move so fast. Is it 3 hours or 4 hours? We started at 9:30.
4 hours.
Oh my goodness. All right.
3 hours, 30 minutes.
Kwa hivyo mmepata bonus. Any question? I know I have another class at 2:30 and it's going to be time series. Any question? Okay. So I'll assume that there is no question. Alvin?
Yes.
Was it worth your time?
Yes, it was. Thank you.
Okay. Was it complex? Was it something you can chew and build on?
It's something I can chew and build on.
All right, perfect.
Yeah.
Devi, I know this was a good refresher.
Yeah, this was nice. Sika hizo zingine ze tumekuwa nao, the other group of the first intermediate class, ilikuwa ngumu.
The first review, eh?
Yeah, so this imekuwa at least friendly. Yeah.
Okay. Okay, that's good feedback. Robin? Robin?
It's been a very good session. I've understood it better than we had dealt with previously. Today I've actually gotten the concepts very well.
Okay, that's good to know.
Yes.
The principle ni ujinga inatoka?
Natoka.
Hata mimi kuna vitu mnaniambia
ujinga.
Tunapunguza ujinga, napunguza tu. Tukitoa ujinga tutaanza kumea pembe, so hatutaki kumea pembe.
Tunaipunguza tu kidogo.
Tunaipunguza tu polepole. That's good. Silas, I don't know if you have a chance to just give a final remark before we close the class. Okay, we'll pass Silas. Deno?
Good work.
It was a good review. I know some of these things you've covered.
Yes.
All right. So I think we'll build up on this in subsequent classes. That will be it for today. We meet again on Saturday. If you want to attend the afternoon class for time series, you're more than welcome to attend. The thing is, you might get lost. Some of these things, but it's good. When you get lost, you have more questions and then you struggle and find yourself away. So until next time, you guys have a nice week, busy week, and continue reading and researching. And I also look forward to you guys telling me what you guys learned through the week. Pia mimi nataka kutoa ujinga ile niko nayo. So please, go out there, read more, and find something new and share with the class. Sawa sawa?
Sawa.
See you guys.